All right, so finding center of mass of a uniform object. We've already looked at finding that the center of mass of point masses. We did that today. And you get the benefit of having the center of mass equation on your AP sheet. So the center of mass is equal to the sum of all the little masses times their positions divided by the total mass. So then we took a look at finding the center of mass of a uniform object, and that's what we just did in practice. You're basically just doing the exact same thing, except that you're doing that with the centers of the pieces of your object, just like we practiced. But more formally, we use this equation where r of the center of mass is equal to the integral of r dm over capital M, which is our total mass of the object. This is not something that's going to be on your test on Tuesday, but I want you to see it because we're going to use this exact same integral, this rdm, except it'll be an r squared, when we're doing rotational motion. So I just want you to see it once before we do that. Chances are not huge that you're ever going to have to use this with center of mass, but I do want you to go through it today, just as a preview. So the tricky part with this is the integral, because usually whatever variable you have here, you have d that variable. So you do, if this was r dr, your integral would end up being r squared over 2, but it's not, it's r dm. So we have to make the dm into something that's related to r in order to be able to do this integral, and that's what's tricky about it. So here we go. So to calculate this, we're going to say that it's in the x direction, so we're going to change all our r's to x's just to make life a little bit better. So you need dm, so that's the issue. So just like the changing mass thing that we did yesterday, we're going to set up a proportion. So the amount of mass, little m, in x amount of distance, so m over x, is proportional to the total mass and the total length. So just like we did yesterday, except it was y. That's the only difference. But now we're talking about a small dx and a small m. So we're looking at dm over dx. So little bitty bits of mass and little bitty bits of distance. So now we can solve for dm. So dm is equal to m over L dx. And so now it doesn't look too horrible. So if we plug that in, so here's our integral, and if we plug in where r is equal to x and dm is big M over L dx, then this becomes our integral. So this part here, so our total mass is going to be the sum of all the little dm's. So if you do that, going over 0 to L, this part here is going to just be m, which is awesome because that's what you want it to be. So you don't really need to do this part, but I wanted you to see it because if it's a mass distribution and not a uniform object, then this is different. So then your center of mass is going to be this r dm. So you're going to have r becomes x, then your dm is m over L dx. The m over L can come out of the integral because it's a constant. So then it's x dx, and we know how to do that. That's not a problem. Yay. And then we can integrate over the m over L dx, and I'll show you what that looks like in the next slide. So once we do this, we're just going to get L. So the sum of all the L's is just L. So that's that one is. And then the top part of this is going from 0 to L, so the whole length of the object, x dx. We get an x squared over 2, evaluated from 0 to L, and then this becomes just x evaluated from 0 to L, so the bottom whole part is just going to be L. This is going to be L squared over 2, and so then my units didn't come out, or I don't know why it has a question mark there, that's just weird, and it says L over 2, so that is your x at the center of mass. So if it's uniform, we just proved that the center of mass is right in the middle of it, which is what we were assuming when we did our practice earlier today. So yay, it worked. So that's good. So now what happens if the object isn't uniform? So generally speaking, they'll give you a linear density. So I have not seen this where they ever have you do this in more than one dimension, so that's good. So you have, let's say our linear density is just some function. If it's uniform, the linear density is just m over L, so mass over length. So just like regular density is mass over volume, linear density is mass over length. So then you go through the whole thing here. So our dm over dx is proportional to that linear density. So if it's a function, then you're going to have a function in terms of x. So dm is going to be equal to that function dx. Okay, so it'll be m is going to be equal to that function dx integrated over the length. So maybe it's only half the length, maybe it's the whole length. It just depends on what they want you to find the center of mass of. And then here, you're going to have the linear density times x dx. And then, you know, if this is a function that's weird, you know, like it could be k x squared or something like that. That's the kind of thing that they would give you for this, which will change what this is. And then you have to integrate with that new x value. So again, remember, we need this dm to be in terms of x or r so that we can integrate over it. And that's where that proportion sets up. So dm is going to be equal to the linear density dx. And that allows you to integrate. So I'm going to go through one example. So here we have now a non-uniform thing. And so if the darker color tells you that it's denser, then we know that the center of mass can't be in the middle anymore because it's got to be towards the heavier end. And how do we figure that out? So they give us a linear density is equal to kx. And then we can solve this thing. So here we go. So we've got the integral, and since we're going for the entire length, we know that the total mass is just going to be total mass m, so we don't need to integrate that part, which is nice, although, oh, actually we do need to, never mind. So forget I said that. So the center of mass is going to be the x dm over the total m. Our dm is going to be equal to that linear density dx. So this is going to be going from 0 to L, x, and then the linear density dx, so it's x dm. So the x linear density dx, the linear density is kx. So that means that we've got, I'm going to take the 1 over m just out so that that's not a part of that. And then here we've got 0 to L, kx squared dx. So the entire top part of this is then going to be kl cubed over 3m. Now we need to find the total mass. So that was the numerator. That was just the top of this center of mass thing. So now we do the bottom part. The total mass is equal to the integral of dm. So that was lambda dx from 0 to L. That's kx dx from 0 to L. That's kx squared over 2. Once we integrate that, evaluated from 0 to L, that's kl squared over 2. Okay, now we can divide those two parts. So we have kl cubed over 3m, and we've got, but that m is now going to be kl squared over 2. So we've got kl cubed over 3, kl squared over 2. So that m has been replaced by what we just did here. Once we eliminate, cancel all the stuff that can cancel, and then multiply both sides, or top and bottom, by 2. So dividing by a half, we multiply by the reciprocal. That gives us 2L over 3. So what that means is that our center of mass is 2/3 down this rod, which makes sense because it's more dense, closer to the L end of the rod. So again, not on your test on Tuesday, but this process is what we're going to use when we need to integrate for our rotational inertia when we're doing rotation. And I just wanted you to see it once so that you have something to build off of when we do that.